Hello, my name is Fox Thorpe. I am with the McCormack Lab at the University of California, Davis, and today I would like to tell you about my research on the thermodynamics of high-temperature materials. To start, I would like to tell you about the dual laser conical nozzle levitator system. This system uses lasers to heat an aerodynamically levitated sample in a precisely controlled atmosphere. This allows us to reach temperatures well above 4,000 degrees Celsius. One application of this is to determine the melting point of a material. We accomplish this by heating a sample well above its melting point and allowing it to cool rapidly. By observing the material freezing, we can then determine its melting point. This device is designed to heat a range of ceramic and metallic materials. It has a 400-watt carbon dioxide laser, which is well suited for oxide materials, and a 500-watt ytterbium fiber laser, which is well suited for metals. Both lasers can be used in conjunction to heat materials that do not absorb either single wavelength well. It also has two single-color pyrometers, one for temperatures from 750 to 3,500 degrees Celsius, and the other for temperatures up to 5,000 degrees Celsius. In the experiment you see here, I am melting a 3 mm spherical ruby sample using the CO2 laser. There's a close shot of the beautiful sample in the tray, and another shot of it sitting in the nozzle. You may be able to see it slightly shake as it levitates in the gas stream. I place the interlock cap on and begin to slowly turn up the laser. So ruby is simply aluminum oxide with chromium defects in it, making it red. So we expect it to have a similar melting point to alumina around 2050 Celsius. I increase the power to the laser and balance the stream of gas. Because I'm melting an oxide, the gas in this case is pure oxygen. When melting non-oxides, I often use ultra-high purity argon to prevent sample oxidation. The sample is becoming fully molten, and I am going to try to reach around 2250 Celsius and hold it at that temperature for several seconds. You can often see the top of the sample melt first, and often a hot spot will be evident directly where the laser hits. Now watch the sample carefully. As I turn off the laser, the sample will begin to cool and glow less brightly. But suddenly, there will be a slight flash. That flash is the phenomenon that I am trying to capture. At that moment, the sample is freezing, and that exothermic flash is known as recalescence. The recalescence is also captured by the pyrometers, as the temperature briefly holds at the freezing point, showing a distinct change in slope compared to the normal cooling. Recalescence is observed in metals and ceramics when there is a phase change. It can be used to identify liquid to solid phase transitions as we saw here, or even solid-solid phase transitions. And here's a quick look at some of the data I have collected for aluminum oxide. You can see here the temperature begins falling once the laser is off. It holds briefly at the freezing temperature and then continues to fall like normal. I have successfully completed this experiment with several oxides and even some high temperature metals such as niobium and tantalum. This melting point data is important to the development of phase diagrams and identifying solidus and liquidus lines in high temperature systems. Development of these phase diagrams is key to advancing nuclear energy systems, hypersonic vehicles, and space exploration technologies. As I conclude, I'd like to thank my undergraduate research assistant, Chad Sarayo, my PI, Scott McCormack, and our funding partners and collaborators, including DARPA, NSF, and the American Ceramic Society. And most importantly, thank you very much for watching. Please feel free to contact me at fhthorpe@ucdavis.edu or foxthorpe@gmail.com. Thank you.